Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 7th, 2025, just yesterday. It introduces a new reward modeling method that boosts preference accuracy on creative writing tasks from about 58% all the way up to 85%. The paper is titled Pre-Trained Policy Discriminators or General Reward Models, and as we'll see, the results are really impressive across the board. The authors propose a new pre-training method called Policy Discriminative Learning, or POLAR, to create more general and scalable reward models. Also, the authors shared their implementation on GitHub. Over there, you'll find their pre-trained POLAR models, including both base and ready-to-use checkpoints. They've also included code for inference and fine-tuning, along with several clear examples to get you started. It's a very complete repository for experimenting yourself. On Hugging Face, you'll find the 7 billion and 1.8 billion parameter models ready to download, with code examples to get you started right away. Alright, so this first figure really sets the stage, comparing the new method to older ones. On one hand, you have traditional reward models that assign an absolute quality score to a response. Then you have rule-based verifiers, which just give a simple pass or fail, but that only works for tasks with a single correct answer. What's new here is their POLAR method. They reframe the problem, creating what they call a policy discriminator, which is a model trained specifically to tell the difference between the outputs of various other models. Building on that idea of a policy discriminator, this diagram shows how the whole process works in 3 steps. First, during pre-training, the system learns to tell whether 2 different responses, or trajectories as they're called, came from the same underlying model, or policy. Then, in the fine-tuning stage, humans rank several trajectories from a single model, teaching the reward model what good looks like. Finally, this reward model is used in a process called reinforcement fine-tuning, where it guides another model to produce better outputs by comparing them to a high-quality reference. Moving to the results, this radar chart really drives the point home. It compares the author's POLAR models, shown in red and blue, against several other strong baseline models across a dozen different tasks. These tasks range from creative writing and coding to STEM and role-playing. The further a line is from the center, the better its performance at predicting human preferences. And as you can see, the red line for the POLAR 7 billion model consistently forms the outermost ring, showing it dramatically outperforms the others, even a much larger 72 billion parameter model. This next table then shows how that preference accuracy translates to actual training performance. It details the results of using different reward models in a process called reinforcement fine-tuning, which is where a reward model is used to guide and improve a main model. We see several different main models here, like Llama 3.1 and QN 2.5. For each one, the authors test various reward models. And the takeaway is clear. When their POLAR 7 billion model is used as the guide, the resulting models achieve the highest average scores across all tasks. Okay, and this brings us to a really important question. How well does this method scale? These 2 plots show the scaling laws for the POLAR pre-training. Essentially, they show a predictable relationship between resources and performance. The chart on the left shows that as the number of model parameters increases, the validation loss, which is a measure of error on unseen data, steadily decreases. The chart on the right shows the same trend with more computing power. The dashed lines show an almost perfect power law relationship, which means performance gains are very predictable. Building on those scaling laws, this next table digs into why the method is so effective, using what's called an ablation study. That's where you systematically remove parts of your system to see how much each one contributes. Here, they compare the full POLAR model against a version without its pre-training step. For both the 1.8 billion and 7 billion parameter models, the results are clear. The full method gets the highest scores, but when you take away the pre-training, performance drops significantly. This result really proves that the pre-training phase is the critical ingredient. So to wrap things up, the big takeaway here is that by changing the problem from scoring absolute quality to discriminating between different AI policies, the authors have created a much more powerful and scalable approach. Their POLAR method, with its crucial pre-training step, builds better reward models, which, remember, are the models that teach an AI what good looks like. And when used in reinforcement fine-tuning, That process of guiding a main model, these polar models lead to huge improvements. That's it for this week's AI Research Roundup. Thanks for tuning in.